Here we show that the sequence 3n divided by n plus 1 is convergent. So let n equals to 3n divided by n plus 1. So n plus 1 equals to, replace n by n plus 1. So we get this kind of expression. Now an plus 1 minus an equals to 3n plus 3 divided by n plus 2 minus a 3n divided by n plus 1. Now simplify this. Cancel this term. 3n plus 3n equals to 6n. 6n minus 6n 0. Altogether we get 3 divided by n plus 2 into n plus 1. That is an plus 1 minus an equals to 3 divided by n plus 2 into n plus 1. Now since n belongs to natural number, this shows that n plus 2 is greater than 0 and also n plus 1 is greater than 0. That is 1 divided by n plus 2 and n plus 1 is also a positive quantity which is greater than 0. Around n belongs to natural number, and also 3 is a positive quantity, that is 3 divided by n plus 2 into n plus 1 also greater than 0. So this is a positive quantity, hence n plus 1 minus an is greater than 0 for all n belongs to natural number. This shows that an is a monotone increasing sequence. Also this is the number one part. An is monotone increasing sequence. Also an equals to 3n divided by n plus 1, which is also can be written as 3n plus 3 minus 3 divided by n plus 1, because when we cancel plus 3 minus 3, then this becomes 3n divided by n plus 1, which is exactly equal to a, which also can be written as, if we take in common from first term and second term, then we have 3 into n plus 1 minus 3 divided by n plus 1. Then we divided both the expression by n plus 1, then we have this kind of expression, and cancelling n plus 1, 3 minus 3 divided by n plus 1. So n also can be written as in this format. Now n belongs to natural number, so n plus 1 is a positive quantity and also 3 is a positive quantity. This shows that 3 divided by n plus 1 is also a positive quantity. Also a positive quantity. So altogether 3 divided by n plus 1 is a positive quantity. This shows that if we multiply both sides of the inequality by minus, then we have minus 3 divided by n plus 1 is less than 0. That is, remove this part. That is, if we add both sides by 3, is less than 0 plus 3, which is 3. That is, now 3 minus 3 divided by n plus 1, we already see that this expression is n, which is less than 3. So for all n belongs to natural number, n is less than 3. That is, n is bounded by an upper bound. So n is less or equals to 3. We also can write n is less than 3 or 3. So n is less than or equals to 3 for all n belongs to natural number. That is, the sequence 3n divided by n plus 1 has an upper bound. This is the second point. So combining this, n is a monotone sequence. This is number 1 point, and the sequence has an upper bound. So we already discussed that a sequence which is monotone increasing and has an upper bound, then it is convergent and converges to its exact upper bound. So combining this and using the previous result, we claim that the sequence 3n divided by n plus 1 is convergent, and here we using the result. Here we using this result, which is already discussed in the previous class. The sequence which is monotone increasing and has an upper bound, then the sequence is convergent and converges to its upper bound. We use this result. The sequence is modern increasing, and the sequence has an upper bound. Then, using this statement, we claim that the sequence is convergent, and hence the proof is complete. Next, we discuss the question. Consider the sequence n plus 1 divided by 2n plus 1. We now show that this sequence is also convergent. So, as in, let an equals to n plus 1 divided by 2n plus 1. So, an plus 1 equals to, replace n by n plus 1, n by n plus 1 divided by 2 into n plus 1 plus 1. After simplifying, we get this kind of expression. So, an plus 1 minus an equals to n plus 2 divided by 2n plus 3 minus n plus 1 divided by 2n plus 1. Simplify this expression. Cancelling plus 2n square minus 2n square plus 5n minus 5n. So we get the expression minus 2 minus 3 minus 5 divided by 2n plus 3 into 2n plus 1. This is the final expression. Remove this part. An plus 1 minus n equals to minus 5 divided by 2n plus 3 into 2n plus 1. Now, n belongs to natural number. So it is obvious that 2n plus 3 is greater than 0, and also 2n plus 1 is greater than 0. So if we multiply two positive quantity, then the product will also be a positive quantity. Since this is positive quantity, so 1 divided by 2n plus 3 into 2n plus 1 is greater than 0. Now, if we multiply both sides by minus 5, then the inequality is changed. Minus 5 into 2n plus 3 into 2n plus 1 is becomes less than 0, and minus 5 divided by 2n plus 3 into 2n plus 1 is an plus 1 minus a. So we conclude that the expression an plus 1 minus an is less than 0 for all n belongs to natural number. This shows that the sequence n where n equals to n plus 1 divided by 2n plus 1 is monotone decreasing sequence. This is the number 1 point. The sequence is monoton decreasing. Next we consider the expression an equals to n plus 1 divided by 2n plus 1. Now it is obvious that it is clear that 2 is greater than or equals to 1. It is very obvious. So 2 plus 2n is greater than or equals to 1 plus 2 for all n belongs to natural number. It is obvious. So if we taking common 2, then we have the expression 2n 2 into n plus 1, which is greater than or equals to 2n plus 1. This shows that 2 into n plus 1 divided by 2n plus 1 is greater than or equals to 1. So n plus 1 divided by 2n plus 1 is greater than or equals to half. So this also can be written as half is less than or equals to n plus 1 divided by 2n plus 1. Now n plus 1 divided by 2n plus 1 is n. So half is less than or equals to n. This shows that the sequence has an lower bound. There exists some quantity which is less than or equals to n. So n has a lower bound. So we conclude that the sequence n has a lower bound. Now combining these two, number 1, the sequence is monoton decreasing and the sequence has a lower bound. So by the result, which is already discussed in the previous lecture, a sequence which is monoton decreasing and has a lower bound, then the sequence is convergent and converges to its lower bound. So by this result we say that the sequence, the given sequence n is convergent. So we show that the sequence n plus 1 divided by 2n plus 1 is a convergent sequence. Next we discuss very important question, so that the sequence root over 2 into root over 2, comma root over 2 into root over 2 into root over 2 and so on is convergent and converges to 2. So first we assume that let n equals to root over 2 or a1 a1 equals to root over 2, a2 equals to square root of 2 root over 2, a3 equals to square root of root over 2 into root over 2 into root over 2 and so on. Now by the given pattern we say that the sequence an is root over 2 into square root of root over 2 into square root of root over 2 and so on. Now if we taking only square root of 2 and the whole part square root of root over 2 square root of root over 2 square root of root over 2 is the previous one, that is a n minus 1. So we will taking square both side to get an square equals to 2 a n minus 1. So if we replace n by n plus 1, we get n plus 1 square equals to 2 a n plus 1 minus 1, which is 2 a n. So a n plus 1 square equals to 2 into a n. Now a n plus 1 square minus a n square equals to a n plus 1 square equals to 2 into a n minus a n square equals to 2 into a n minus 1, that is a n plus 1 square minus a n square equals to, taking common 2, so we get a n minus a n minus 1, this kind of expression. So we add a n plus 1 square minus a n square equals to 2 into a n minus 1. Now we apply here the formula a square minus b square. I know that this is a plus b into a minus b. So this left hand side can be written as a n plus 1 plus a n into a n plus 1 minus a n equals to 2 into a n minus 1. Now we see that when this part is a positive quantity, then also this part is positive, altogether positive, and since a n equals to root over 2 square root of root over 2 into square root of root over 2 into square root of root over 2 and so on. So each of the sequence an is a positive quantity and also n plus 1 is a positive quantity. So this part is always a positive quantity, and if an is greater than an plus 1, then right hand side becomes positive, and this is positive for any n. So when this part is positive, so obviously this part is also positive. Now an greater than n plus 1, this shows that right hand side becomes positive quantity. Now this is a positive quantity, so altogether the expression is positive, and this expression is already positive, so this expression must be positive. An plus 1 minus an is positive quantity, that is n plus 1 is greater than a. So this a greater than n plus 1, this implies that a n plus 1 is also greater than an. Now we are checking that this part is a positive or not. Now a1 equals to root over 2, a2 equals to root over 2 into root over 2, and so on. a3 equals to square root of root over 2 into root over 2 into root over 2. So from the observation we basically see that for any an, the inequality a3 is greater than a2. Since this part is numerical value of a3 is greater than a2, and this a2 is also greater than a1. So if we see the pattern, we also can be written this kind of expression, and so on. That is, a1 is less than a2, a2 is less than a3, a3 is less than a4, and so on. This shows that the sequence an is monotone increasing. Rather, we can say that this part is strictly increasing also. So this is monotone increasing. So this part is whole, and so this part is also. So the original sequence is monotone increasing. This is the first part. Next we show that the sequence has an upper bound, and so by the previous result we can say that the original sequence is convergent. Now we already see that this kind of expression is called, which is already proved this part. Now since an is monotone increasing, so an plus 1 is greater than a. So combining 1 and 2, so from 1 we already get this expression, n plus 1 square equals to 2 into n. And from 2 we have an plus 1 is greater than n. Now if we multiply both sides by positive quantity 2, then the inequality becomes 2 into n plus 1 is greater than 2 into n. and from 1 we already see that 2an is equals to an plus 1 square. So this shows that an plus 1 square is strictly less than 2 into n plus 1. So n plus 1 square minus 2an plus 1 is less than 0. Taking common n plus 1, so we have n plus 1 minus 2 is less than 0. Now an plus 1 is a positive quantity. We already discussed previous. Since n plus 1, a1 equals to root over 2, a2 equals to root over 2 into root over 2, and a3 equals to root over 2 into root over 2 into root over 2, and so on. So in each case the term a becomes positive, so this part is positive. So this part is always a positive quantity. And from this expression we clearly see that an plus 1 into an plus 1 minus 2 is less than 0. That is, altogether the term is negative and this part is positive. We know that plus into minus becomes minus. So this part cannot be plus, because if this part is positive quantity, then plus into plus quantity becomes greater than 0, which contradicts the inequality. So by logic we say that this part is minus quantity, that is an plus 1 minus 2 is less than 0. That is an plus 1 is less than 2. For all n belongs to natural number. Now this word for all n belongs to natural number. So if we replace n plus 1 by an arbitrary natural number n dash, we say that an dash is less than 2 for all n dash, which is also a natural number. So you get this kind of expression. This shows that the sequence is bounded by a positive quantity, which is 2, or we can say that the sequence n as an upper bound. Now combine these two results. The sequence A has an upper bound and the sequence is also modulo increasing. So by the previous stated theory, we say that the sequence which is modulo increasing and has an upper bound, the sequence is convergent. This is the first part. The sequence is convergent. Now we show that this converges exactly to. This is is the first part. Second part. Now we show that limit n tending to infinity a n equals to 2. Now we assume that since this is convergent, so converges to a finite point, so let limit n tending to infinity a n equals to n, and here is finite obviously since this is convergent. Now since it is convergent, so n becomes infinity, so also a n plus 1 is n. Since n becomes infinity, this tending to n, so when we replace n by n plus 1, then the value becomes same, that is limit n tending to infinity a n is also convergent to n. Now from the previous expression we see this kind of expression a plus 1 square equals to 2 into n. Now taking limit both sides, taking limit both sides, we get limit n tending to infinity a n plus 1 square equals to 2 limit n tending to infinity n. Now since limit n tending to infinity n plus 1 tending to n, so limit n tending to infinity n plus 1 square tends to n square. Since by our assumption limit n tending to infinity n plus 1 equals to n, and this part tending to n, since by our assumption limit n tending to infinity a n equals to n. Now solve this expression, we get l square minus 4 equals to 0. Taking common l, we get l minus 2 equals to 0. Now since l equals to limiting value of the sequence a, and each a1, a2, a3 and so on are non-zero quantity, so l is never 0. So l minus 2 equals to 0. Since l is a limiting value of the positive sequence, so it never can be 0. So l minus 2 equals to 0, and solving we have l equals to 2. This shows that the sequence is convergent to n, that is limit n tending to infinity a n equals to 2, and our proof is complete. So we stop the lecture here, and in the next class we discuss about some concept of series. And if you have any doubt, then please join the Telegram group. So we stop there. Thank you.